When programming, we often have to store collections of information. For example, this could be a list of user accounts on a website or queued posts for social media. While there's a lot of data structures we could use, the humble linked list is often the most handy. In an array, you must predefine the number of elements. Lookups and appending take constant time, but there are downsides. Random insertions are very complex, as the entire array must be shuffled. Also, once you exceed capacity, the array could be copied to a new part of free memory. Languages like Java use structures like array lists, and this masks the complexity of growing the array. But sometimes it is more appropriate to use a different data structure. In this example, we want to add Rick to the list of users after Tim. In the array, we must first grow the array by copying it to a new part of free memory. Move all the users down, and then add Rick in the free slot. The linked list works very differently though. Every element in the data structure not only contains the data, it also says where you can find the next piece of information. Inserting a record into the middle of this chain is simple. You simply say that after Tim, Rick comes next, and after Rick, then comes Bill. The records don't even have to be next to each other in memory. The whole thing works because of the ability to use pointers. Implementing this in C++ will give you an overview of how this works and how they can be used. And obviously, there's libraries to do this for production code, but it's also great practice to learn from first principles. I've created a new linked list class which describes our overall data structure. Part of this is an additional structure which describes the repeating bit, called the linked list element in my example. We also need to store some data. This could be something like an int or a string, so let's template this out and call it t-element. This means we could use something else in the future. The linked list element contains 2 pointers, one to the next element and one to the previous element. So this is actually a double linked list. A single linked list would only contain pointers to the next element. We'll make the linked list element private, as we don't really want anyone to use this, but we can make a public constructor instead. I'm assuming that this will just create an empty list, so I'm not going to add any parameters here for now. I'm going to include this file in my main.cpp and instantiate one linked list instance. I'm using the auto keyword here, but the new constructor is basically creating a linked list star. In the future, we'll be parameterizing this as well, but we're not going to do that just yet. If we try and compile this now, we'll get an error. This is because we've declared stuff we haven't actually defined. We've got this linked list constructor, but there's no body for it, so I'm going to add that now. And oops, I just forgot, we need to add some type parameters here as well. In our linked list, we're going to have a chain of data which references each other, but we need a starting point, like the first element in the list. And so this is going to be called the head. This is going to be parameterized by TList, and I'm going to add this template to the top of the class here as well. This involves a couple of minor changes, and we'll initialize this with a null pointer. Yes, I also need to template this method. And yes, I also need to change it in the main.cpp file as well. But this gets it working. I'm going to do some unit tests while I'm writing this linked list as well. While some developers like to debug all the output to the console, it's quite nice having repeatable tests which the compiler can say whether things work or not. I'm going to use Catch, which is a nice simple one-header library. I'll just download this and import it into my C++ project. I'm being quite lazy in how I'm importing this. There are some tools to manage dependencies, but as we only have one, it doesn't really matter in this instance. I've deleted the main file in my main.cpp and defined catch config main instead. Catch has its own main, which will run our tests automatically. So all we have to do is define a series of scenarios. So I'm going to just call this one linked list tests, and my precondition is going to be an empty array linked list. Now, if our data structure is designed to store information, a good place to start is by adding information to our data structure. So I'm creating this function called Append, and this is going to add something to the back of our link. So if the list is empty, we first need to set the head element, which defines the start of the chain. I want to define this as a new linked list element, but because it's a struct, there's no constructor for it. So I'm just going to create a new object and then assign the data to this element. I need to first also set the next and previous to null. This code looks really useful, and it seems like something I'd use again, so I'm going to copy this out into a function. And for now I'm just going to call this something like make element and return a linked list element from this. When I'm passing data to this function, I'm both making it constant and passing it by reference. This means we're not copying the information, and the const guarantees that this function won't change it. So now, instead of creating this object by hand, we can now just call make element every time instead. I'm using the auto keyword here instead of the definition, and this just means if I need to change anything in the future, the compiler will infer the type at compile time instead of me having to change it again. So we've done a check and created the head element if it's not already been initialized. But if there's something already there, then we need to add our item to the end of the chain. Now we could start at the head of the chain and go through the entire thing, but that would take linear time with the number of elements. So if there's a million things in our list, then it will take a million time steps. Instead, I'm going to add this new tail linked list element as well. This will be a pointer to the last thing in the chain, which we can maintain while we add new items. So I'll also initialize this. So now all I need to do is update the last item to point to the new element, set the previous element of our new item to the last item, and then finally set the last item to our element. And we've got to be a bit careful about this, so we'll add some tests in the future. So we've made a function to append, now we can just add another one to prepend, and we'll do this later, but it'll just be a trivial reordering of what we've already done. And we'll also add a size function to get the number of elements in our array. So let's start writing some tests. I'm going to start with a condition with an empty list, and when I append an item, I'd expect the size of the array to increase. So I'm going to append this 0, and then make a test case to check whether the array size is 1. Note there's like a minor mistake here. Note that there is a minor mistake on line 17 here. The check to see if the array is empty should appear before I add the item, not after I add the item. But for now, I start working on the body of the size method instead. So the way I'm going to do this is have another variable tracking how many items are in the list. But there's a more inefficient way I'm going to implement just to show you how not to do it. And this will be to iterate over all the items in the array and count them. So I make an integer to record the size and call this list size. Then I'll get the first element from the head and iterate until I've found something which is the null pointer, which represents the end of the array. Then I'll just return the number of things I've seen by counting +1 every time. But instead, what I'm going to do, this bug here is what I mentioned about from line 17 where the test is wrong. It took me a couple of minutes to fix, but it's fine. All our tests pass and run now. So now let's simplify it and just use the number of items counter instead. I'll also implement the prepend here. It's just swapping the previous and the next around. Let's add a test for this and another one for both when I append and prepend, checking that the list size is 2 here instead of 1. So after it compiles and all the tests run, I realise I forgot to initialize the count variable. So I'll go back and do this now. And it looks like we're back in business. Now we've verified that that works, we can start getting data out of our linked list. So I'm going to implement the subscript operator. So this might look a bit scary, but really it's just a function which overrides an array lookup. So I'm just going to let that return null pointer for now and start creating some tests. I want to add some data into the array and then verify I can get it back out in the right order again. So I'm just going to copy and paste a couple of things and check it runs. But I've just realised actually that I can't return null pointer because it's a special type in C++. So I'm going to come back and fix that later. And instead I'm just going to implement the body of this function. I just start with the head element and then iterate until I find the nth element I want. I'm going to use a for loop for this. So I have this index which I'm keeping track of and I'll stop when I reach the desired position. So to get the next element, I just simply look at what's in found and set the found to the next item from that found one, if that makes sense. Once I've stopped, I'll just return the data I found, not the linked list element. And just got a couple of minor things to fix. So run that, and my test passed, which is good. I just realised some of this stuff is public when it shouldn't be, so I'll move it into the private section. Another couple of operations you might want to do on a linked list to remove data and insert something at a random position. By random, I just mean at the nth position rather than at the beginning or the end of the list. We'll start by implementing remove because a lot of the principles in remove can then be applied to the random insert. So we're going to need to find the kth element of the array list. So I'm going to reuse my code and create a new function called getElementAtPosition. Once I found the element, then I can look at the ones either side of it and link them to each other. So there's a couple of minor fixes to make after copying and pasting. So now that's done and working, I'll get the elements before and after the one we've just found. When we delete this item, then we'll join the before one to the after one, but we need to check they're not null first to avoid any seg faults. If the element we're deleting is the head or the tail of the linked list, then we'll also need to delete this. It was a bit of a strange thought exercise working out which one I need to delete and how to reassign these values, but I got there in the end. Because it's a bit confusing, I'll add a few comments and then I'll delete the element we've just removed from the linked list. I'm just going to use the C++ delete command here instead. and remember to decrease the number of items we've got in our array. There's a couple of minor type issues I need to sort out here as well. I blame the editor. Basically what's happening is doing code generation, but it's getting the templating wrong. But at least it works and builds now, and all our tests pass, which is good. There's a few more test cases I want to add, after just tidying up a few of these bits of code. So the first case I'm going to add is when I start with a list with 3 items, and then I delete one of the items are still in the correct order. And this is just to verify that I don't accidentally rearrange some when I swap the items around. So I'm creating 3 test cases when I delete the first, second and third item. Let's test the boundary cases. So now I'll create the method for the insert, only to have Jetbrains crash on me when I try this. It's a bit annoying, but these things happen. I don't trust the code completion, so I'll write this method signature by hand instead. When we insert something at a random position, we firstly take the data item, and then a second argument for the position in which we insert it to. This method's slightly more complex, so I'm going to start by writing out what I'm going to do in a comment. So if I've got a list with these 4 items, and I want to insert before the second item, what I'll do is set each of the next and previous pointers on these to the new item we're inserting, and then set the next and previous pointers on our new item to those ones there. So now I know that information, I can quickly implement this. And this should save some trial and error. I just start writing these now, but later I'll need to add some checks to see if these are null. If the item before this one is null, then I'm not going to bother setting the next pointer on the previous item to the new one I'm inserting. If the position given to me is the last item or the end of the list, then I can't really insert it in this manner. So in that case, I'm just going to append it to the list instead, as I'll effectively be doing that. And if I'm inserting this item to the beginning of the array, then I also need to remember to update the head as well. And finally, just update the count for the number of items in the list. That's it. So finally, the last thing I'll do is add a few more tests to check that when I insert items at random positions, the order of the list is preserved and the items appear in the correct place and the count is updated. I get this wrong a couple of times, and this is because of copying and pasting, but it finally compiles and all 39 assertions are correct. So that's it.